we can see metal insulator semiconductor structure energy band diagrams. So already you have studied in electronics paper and VLSI paper about MOSFET structure. Okay. Similarly, here we are going to see MOSFET structures and the related energy band diagrams. So generally MOSFET is nothing but a metal oxide semiconductor. The oxide acts as an insulator. So the structure states that metal insulator, this is silicon dioxide layer, then semiconductor. This semiconductor can be either N type or P type. This is the width of the insulator. For an ideal metal insulator semiconductor diode, the energy difference is, that is metal and semiconductor, is denoted by this symbol between the metal work function phi m and the semiconductor work function psi s is 0. So the metal energy difference between metal work function and the semiconductor is defined like this. The psi m is the semiconductor work function, x is the semiconductor electron affinity, Eg is the band gap, energy band gap, psi b small and capital. So psi b is the potential barrier between the metal and the insulator. Capital psi b is the potential difference between the Fermi level and the intrinsic Fermi level Ei. The Fermi-Dirac function. So the Fermi-Dirac function is nothing but f of E is equal to 1 divided by 1 plus exponential E minus Ef divided by kT. K is the Boltzmann constant, T is the room temperature, Ef is the Fermi level, E is the energy diagram. So this is the energy diagram for the metal insulator semiconductor if it is in unbiased condition. You take a metal, so this is the the level, okay, minimum level. So from the minimum level to the maximum level, vacuum level, denoted by Q pi m. This is work function. Similarly, this is insulator. D is the distance between metal and the semiconductor. Okay, so this is the level of valence band. The dotted line represents the Fermi level. This is intrinsic semiconductor energy. This is conduction band for energy level. The Qx is nothing but the work function of the conduction band. Q pi s is the Fermi level work function. Eg by 2 is the Eg is the energy band gap, okay, divided by 2. That is, this is the distance between intrinsic semiconductor and the conduction band. Q psi b is the difference between Ei and Ef. So this is in unbiased condition, no supply is given. Here how the things is happened, the level of the each and every band. P substrate. This is the semiconductor is taken as a P-type substrate. Okay. Once the negative bias voltage is applied, negative bias means that is for P negative, metal connected to the positive. So what will happen? You look at the energy band. So it's getting down. You look at it. So compared to the previous slide, okay, the equilibrium status changes its the bend shape. You look at the bend shape. Okay, so this is the Fermi level Ef in the semiconductor is now minus QV below the Fermi level in the metal gate. So this has happened when a negative bias is applied. When a small positive voltage is applied, plus minus, you look at it automatically. The energy band diagram, it is in the reversed state. Okay, the Fermi level of the metal is coming down. So you look at the shape of the energy band diagram for the small positive voltage is applied. If the applied voltage is increased sufficiently, the bands bend far enough, Then level EI at the surface process over to the other side of level EE. This is brought about by tendency of carriers to occupy states with the lowest total energy. In the present condition of inversion, the level EI bends to be closer to the level of conduction energy band and and electrons and number of holes at the surface. So energy bands in the strong inversion. Strong inversion means high voltage is applied. So EI at the surface is now strong voltage is applied below EF by an amount of energy equal to 2 psi B. Psi B is the potential difference, the Fermi level EF and the intrinsic Fermi level EI in the bulk. So the value of capital B necessary to reach onset of strong inversion is called the threshold voltage. So this is about the energy bands basics. Thank you.